Okay. Mark and Susan told me I had to do this. So how do we do this now, Mark? Do they guess? Okay. I got to meet President Obama. Who believes that's true? Okay. I was the social chairman of my sorority in undergrad, uh, and I appeared on an episode of Most Evil on the Discovery Channel.
All right, how many of you think that meeting President Obama is a bald-faced lie? All right, people believe you for that one. So Elizabeth was the social chairman of her sorority in college. That is true or false? False. False. Ooh.
I don't look social. Yeah. They don't know me. So Susan can attest to my social skills.
Is she lying about being this kind of evil?
Okay.
Well,
The
we have a consensus.
right.
Voting for President Obama.
I didn't. I wish so badly that I had. But I was social chairman for my sorority, Kappa Alpha Theta. Thank you very much. I was a charter member at UC Irvine way back in the 80s. Yes? You were at Kappa Alpha Theta too? Okay. And the most evil, it was maybe 10 years ago in Discovery Channel. It was when I was still at UCLA. Asked if they could interview me about adolescent brain development, and I was really excited and proud of the filming and what I did, and they showed me. And then my sister called me about a month later and said, "Liz, I just saw you on Most Evil on the Discovery." So unbeknownst to me, the focus of the piece was on juvenile justice issues, and they were talking about evil teens, and they used my piece to sort of talk about the teen brain. So I was proud of what I did. I was just kind of embarrassed that it was Most Evil. Okay. And I thought I was going to meet President Obama because a friend of my husband's from high school actually went to law school with Obama, and he was in Obama's administration. My friend ended up being the ambassador to the Czech Republic, and we went and stayed there and everything. We went to visit our friend Norm, the ambassador, in Washington, and he gave us a tour of the White House. And I was just somehow expecting President Obama to be walking down the halls, but unfortunately. Okay, so I'll admit, most of the talks I give focus on the data and the results, and so when I agreed to do this for Susan, I thought maybe I would be talking about sort of a accumulation of results and sort of painting pictures about brain development. She said, "Oh no, method. It's got to be about methods." So I'm going to do my best to help just give you some tidbits. In 1 hour, there's no way to give you the whole world of imaging kids' brains. But anyway, between the ears, it is a construction site. Lots of stuff is going on in there. And after 25 or 30 years of imaging, not 30, okay, 25 years of imaging kids' brains, I think I have a little bit to impart to you on what kinds of things, at least that you need to think about if you decide to embark on doing developmental imaging. So just an overview of what I'm going to talk about, and I encourage questions throughout, is just, kind of recruitment. It's a little bit different than bringing in your favorite undergrad class into the magnet and scanning them. Talking a little bit about consent and dissent, challenges in acquisition. There are different challenges in studying children. So motion is the biggest one, the biggest challenge. So I'm going to talk a little bit about how to deal with motion and image processing after the fact, and more importantly, probably looking at prevention. And talking about other issues important, talking about task difficulty for kids. I'll talk a little bit about that. Metal in the mouth, big deal. Braces, happens all the time. And then I'll do my most favorite thing is talking a little bit about the payoff and what kinds of results we're seeing and how it's interesting, and hopefully give you an idea, or maybe to even recruit you into developmental neuroimaging, because lots of people care about it. So recruitment, you got to think about it in a sense that it's, you're recruiting the parents, for the most case, depending on the age. And I'll be honest, I'm focusing mostly on childhood and adolescence, and not on the infancy and early childhood years. But really, it's the parents consenting. It's the parents interested. And you have to just think about things like what motivates parents to want their kids in a study. And I can tell you just from experience, for many years at UCLA and then at Children's Hospital. So UCLA Westwood, very wealthy area. CHLA is in Hollywood. It's got a very diverse surrounding. And in my experience, we've had very different motivations from parents. So I can tell you in UCLA, when I was recruiting here, the diversity was very low. Most of the kids were very high SES. Motivation tended to be more, and these are convenient samples, right? Not trying to recruit a representative sample. But anyway, it was parents who wanted their kids to sort of understand what research was, or something's a little off about Johnny. I don't know. There's nothing diagnosed, but maybe if we could get him into the study, we could figure it out. So anyway, and then at CHLA, I'm sure there's the same stuff going on. Something's a little off about Susie. Let's, see if we can get her into the study. But a lot of it is about the money. So these are lower income, lower SES, and I suspect that some of our families are there to have extra money to buy groceries. So anyway, just things to think about. You're not really recruiting the kid. You're recruiting the parent because the kid has some sort of characteristic that you're interested in. And these are, in the ones I'm talking about are mostly typically developing kids, but also same considerations when you're recruiting children with neurodevelopmental disorders. So I do a lot of studies of kids with fetal alcohol, which I'll talk a little bit about. But that recruitment is very hard in that category, and something else to think about, because most of the kids who are seen in clinics for fetal alcohol spectrum disorders are not with the biological family, right? So they're in adopted homes or they're in foster care, and foster parents don't have legal authority to consent for their children to participate in studies. So there are challenges. I'll talk a little bit more about LAUSD, and it might be just more of a local issue, but since '97 at UCLA and then at CHLA, every person, Susan included, that I would ask, help me figure out how to recruit these typically developing kids. And first thought, go to the schools. Well, that is not so easy. LAUSD, notoriously difficult to get permission to do studies. The kinds of studies historically that they've allowed have had to do with intervention, drugs of abuse, those kinds of studies where it would actually help them and help the individuals. But recently, for the Adolescent Brain Cognitive Development Study, which Susan and I are co-PIs for the LA site, we actually got them to approve to let us go recruit. So Susan and I each got random lists of schools within a certain catchment area, and starting in about 3 weeks, we'll be mailing recruitment flyers to the principals of these random schools. So anyway, ABCD collectively, 19 different sites around the country, all of them will be recruiting through schools. So we really get a representative sample and not the kind of sample that I just talked about, either UCLA, upper middle class mom wants either to know what's wrong with Johnny or wants Johnny to have research experience so he can get into Harvard. I already mentioned this a little bit, but just again, another thing to think about is the children are not, they can't consent for themselves legally, but they do have to provide assent. And so as a researcher, you kind of need to gauge whether the kid really understands it. Does the kid really want to do this, or is it the parent pushing them? And so anyway, just things to think about. They're not just little undergrads. And I think a lot of, especially cognitive neuroscience, neuroimaging happens in undergrads or, convenient sample of adults. So just things to think about. But one thing for sure is that in all of the IRBs that I've had and of colleagues that I know, MRI is typically considered minimal risk. So it's not hard, at least in the US, to get permission to do studies. But, just things to think about if you're going to think about going into pediatric neuroimaging. So this may be true for a lot of populations, but it's much more so an issue when you're dealing with kids, how to get motion-free scanning. So it is the number one concern. I'm participating in a pilot study before we start the big, massive ABCD study. And if you don't know what that is, I will show you a movie in a couple of minutes, and it'll make more sense. So doing a pilot study of kids across, I think, 14 sites, and what are we going to do with the pilot data? Well, the first thing any of these 20 notable pediatric neuroimaging people said, well, the first thing they said that we need to figure out is, are we getting motion-free data from the kids, 9 and 10-year-olds that we plan to study? So data loss, money wasted, right? People don't think as much about, when you're doing these grants, these studies that you get NIH money to do, they're not cheap, right? I mean, you're spending $500, $600, $700 an hour for scanning, and if you're getting crap data because the kids can't sit still, it's not just that you're not getting the data, but you're essentially throwing money down the drain. And I would imagine the proportion of data loss, well, I know, I'll show you, the data loss in children is much higher than data loss in your sort of typical age range, more adolescent and adults. So, the question, and I don't know if anyone's talked about this in your course already, but issues of motion and functional MRI, in particular resting state, and maybe DTI, motion can look like a meaningful signal. And there have been a lot of papers published that are now sort of questionable because colleagues or scientists in the community figured out, yeah, motion can look like real signal that you're looking for. So I'll talk a little bit about that, but by no means am I an expert in post-processing, but I just want to give you an idea that there may be things you can do with, particularly with functional MRI. And structural scans, the kid's in there for 9 or 10 minutes to get one data set, right? And so it's not like functional MRI, we have a bunch of quick TRs and you get, a whole volume every, 30 seconds or whatever. With the T1 weighted high resolution structural, you get one shot, and if they move in the middle of the 12 minutes, it's kind of like, down the drain. There may be some ways to save it with things like real-time motion correction. I think you might, or at UCLA, I think they might have some of that software, but there's software that can allow the magnets to sort of understand motion as it's happening and sort of correct for it. That's the level of my expertise in that area, but there are things that can be done on Siemens and GE, but not Philips. And yes, my magnet platform at Children's Hospital is Philips, so I have to do just a really good job. So this is, just a slide that actually was shown yesterday on the ABCD pilot data call, where, working with this, sort of plethora of experts in both neuroimaging, but who can really focus on developmental neuroimaging. So just showing ways that we can correct for movement after the fact. And this stuff does work on the Philips system. Anyway, I don't have a lot of details, but just thinking about ways to correct for motion after you get the data or even during the scan. So what does motion look like? You probably all have seen what motion looks like. Is there a pointer? Yeah, okay. So anyway, this is, a really good scan of a kid. This one has some slight rings that you'll see from a teeny bit of motion. And in my lab, when we do visual inspection for quality control, and these are for T1 weighted images. And if it's a 1 or a 2, we keep it. If it's a 4, it's gone, right? And if it's a 3, it's pretty much gone. So it's hard to get, meaningful information from the kind of artifact that occurs when a child moves in the scanner. So another kind of issue that we deal with, which I don't think you think about when you study adults or even later adolescents, is kids, they end up in the scanner, whether they move or not, they're placed in the scanner differently. So their heads are really big compared to the size of their bodies. And so when they're in there, where's my little arrow? you can see that their bodies are so small, their shoulders are small, that when they're laying down on their backs, their heads tilt forward. And that's just because their bodies are so small. Where you don't have that kind of tilt in people with bigger bodies. So anyway, it's just something to think about, and this is typical. This is way off. Someone should have gotten the kid out of the scanner and repositioned the head, because, that's really bad. But I'm sure there are consequences of this sort of different plane that you acquire data in children relative to adults. And the only thing that comes to mind really is, in homogeneities within the magnetic field, and are those things in different places in the brain in kids, because when the data is acquired, they tend to be in different places. So I alluded to this a little bit. Motion can look like signal, and particularly I think they've investigated this a lot in resting state MRI. But essentially, published data showed that short distance connections were strong and longer distance correlations were weaker. And then in children, and then as they get older, the longer distance become more robust and less so in the shorter distance. But more recently, mostly Jonathan Power, I think his name is, Power is his last name, really showed pretty cogently that motion adds spurious variance and tends to be more similar at those close networks, short distance networks, than long distance networks. So you can see how that might put into question findings from resting state data in kids, or in typical kids versus kids with neurodevelopmental disorders, because you would think, and I'm sure that there's data out there to show that, well, and I probably have data myself, showing that kids with neurodevelopmental disorders of any kind, or who aren't perfect little angels, statues still in the scanner, if they have behavioral problems, for example, you're going to have more motion than you do in the super bright, really motivated, typically developing kids. So, you can get the wrong results. And this is a study from Power, again, in adults, but you can show here, I think on the top is showing motion in the X, Y, and Z planes within a volume. And remember, you're catching 120 volumes in a typical fMRI scan. So you have that, which is probably would look very similar to the motion I showed you in the T1 weighted images. But then you also have problems of motion between volumes. So if the kid sort of tilts or moves up, they might be very still within a TR, but between TRs they could jump around. That is my understanding, is that that between volumes can be corrected a lot more easily than within volume motion. But as you can see in just adults, with high motion, here I am again, I can't see Susan because I left my glasses in my purse. I'll do my best. Because the screen on here is so small, you get to be my age, that I can't see the small print, and then when I look up there, it looks blurry. So anyway, I'll get through it. But anyway, this, I believe, is high motion adults, and this is very low motion in adults. And you can see you get really different answers depending on motion. Now did you find my Pradas? I was at a restaurant with Susan 10 years ago, and it was dim light. We were at it's probably dinner for a class like this. And it was dim light, and I'm looking at the menu. I'm like, I can't see anything. And Susan's like, oh, here, try these on. And I tried it on, and it was like, whoa, I can see. And they're just reading glasses. And I said, well, Susan, where'd you get those? Did you get them at, CVS? Elizabeth, they're Prada. There's the truth, all right, Susan? Okay. So anyway, you can see the differences in high motion adults versus low motion, and you can get different answers based on just motion, and you wouldn't want to interpret that as meaningful signal. So there's this new thing, or relatively new, that everybody is doing, and I don't think I've seen a paper in the last 3 years of fMRI or resting state where the authors haven't used the word scrubbing in the methods to deal with motion. And so again, I'm not going to, I don't even know how to go through these processes, but I have postdocs in my lab and research assistants who know how to do it. So scrubbing is a word that you often see. Another approach to dealing with motion within particular in resting state. So in the ABCD study, I think things can be moving. The zeitgeist, I think I use the word zeitgeist because people who do resting state have, and who that's their major modality of imaging, have sort of put a weight of importance on it that maybe people like me who have spent more years looking at structural and DTI than, anyway. So somehow the resting state people convinced the whole ABCD consortium that we needed 20 full minutes of resting state data to get 12 good motion-free minutes. So one of the problems is the kids hate it. So we're doing these pilot studies. So far, I think, we haven't started recruitment for ABCD, but I think about 30 or 40 kids across 14 sites have gone through the whole procedure, and this is what they hate the most. Imagine, it's like it becomes sort of a vigilance task. How, stay still, look at nothing, don't think anything. And for kids, it's really hard. And so you do 5 minutes, and then the scan stops, and you say, okay, we're gonna do another 5 minutes. Well, from the anecdotes we've been hearing, the kids are like, I don't want to do 5 more minutes. Get me out of here. So another thing you have to balance is kids have a different level of attention span and willingness. They're not just undergrad college students. They have different levels of attention and willingness to cooperate. So anyway, we are actively discussing in the consortium whether or not we can really afford to lose kids because they don't want to do it. They like the activation paradigms from what I've been hearing, but the resting state is horrible. Now, I have seen some studies or I've heard talk about some studies where it's potential to do resting state where kids or adults can look at some sort of thing on the screen that moves around, right? But there's no pattern to it, but it's better than just staring at a blank crosshair for 20 minutes. So this seems to be a potential promising where, presumably you'd get visual cortex activation, but if you have the same effect of that in everyone, then maybe you can get something out of it. The other thing that I have, interested in looking at, if we're doing, another 40 minutes of functional activation tasks, what about deconvolving the rest from the activation, and can we, out of that, get 20 good minutes of informative resting state? But things to think about when you're dealing with kids that are different than grown-ups. Preventing motion is probably the best idea, and so it takes time. But we, in our studies, ABCD and in our other studies, we have a mock scanner, and we do, it simulates the noise of the scanner. We actually have the goggles, so we can, and we have head motion trackers. So in our mock scanner, we have something that straps to their head, and it measures motion, and we desensitize them and train them to some level of motion-free tolerance. But I have colleagues who have actually somehow devised to literally tape a Wii thing, the Wii wand, whatever on Wii that tracks motion, to tape it to the kid's head. And then there's, it's really cheap, right? Who doesn't have a Wii that's sitting in a cupboard that probably doesn't get used very much anymore? So it's a lot cheaper than these sort of commercial head motion. And if anyone wants to know how to do it, I'll connect them with, I think it was BJ Casey at one of our meetings who demonstrated with a Wii taped to her forehead. We're not proud. Other things you can do, in our magnet at Children's, we have a lot of stickers on the walls that come off because, God forbid, you should ruin the walls in the magnet room. But lots of things to try to make it less clinical, so it doesn't look like this big sort of machine in a medical center. Our magnet's in the hospital, so do everything we can to try to make it less anxiety provoking, and so you can make it look like a rocket ship. Like these people did. I've also seen and want to buy some sort of projection that where you can, from outside the scanner, you can project some sort of laser lights onto the bore of the magnet to make it just look prettier and less scary. So, data from others, Just to prove it, in this study where they looked at 4 to 5 year olds, 5 to 6, and relatively large samples in there, you can see 84% success. That would be, quite a bit of money down the drain. And then the success rate goes up, right? I'm sure if you did into adulthood, well, these 9 and 10 year olds did pretty well first time, but you can see it sort of incrementally, success rate goes up as you get older. But after training, at least in this sample, the second attempt, actually they had successful data 100% of the time. And these are pretty young kids. You probably have to spend a lot more time in a mock scanner with the 4 and 5 year olds than you did with the 9 and 10 year olds. But anyway, to show you that one approach that's probably best if you don't want to throw money down the drain is to do some sort of desensitization training. Another thing that Susan has talked about is sending families home, and I think this is when they do the younger babies, but sending home a tape recording of the magnet sound to just really try to desensitize them as long as you can at home before you bring them into the magnet environment. Task difficulty is another issue, and it lots of ways to figure out how to deal with task difficulty. I think in developmental neuroimaging, so like just an example, you think of if you're studying kids with fetal alcohol versus unexposed controls, even if you're doing just like neuropsychological tasks, you have to wonder if you aren't matching these kids on general intellectual ability, which is hard to do. It's hard to find normal kids who have an IQ in the range of kids with, say, full fetal alcohol spectrum disorder. So anyway, things to think about. Are you really looking at the same thing? Just different approaches. There's lots of creative approaches, but one example is, if for an N-back sort of paradigm, maybe 1-back performance equals 2-back. 1-back performance on younger kids might equal, percent correct of 2-back on typical kids. So you can try to sort of make your paradigms shiftable in that way. Another thing to think about is maybe, implicit tasks could be a way to go. So in this one task that I've been working on for years is, you're asking the kids not to read a word, but to just press a button if there's a tall letter. So like a tall letter would be an L or a T. So you have real words and pseudo words. So that, that's another thing you can do, implicit tasks. Maybe that's not the best example, but and then you can try to control for correct response trials, but then you have to consider how many, in functional MRI, obviously, how many volumes you're losing for incorrect tasks, and then you have to figure out, are you really getting the same, are you comparing apples to apples or apples to oranges? So things to think about that I think you don't have to think about as much when you're looking at adults. The other big thing that everyone knows, it's kind of like the elephant in the closet, is when you're studying kids and adolescents, particularly if it's a longitudinal study, you have to worry about the braces because they happen, and they're happening younger. This is, I'm not sure this is really typical of braces. That's what it said online. And this is not a scan of this kid. This is my kid. And he got braces, just little non-removable spacers when he was 10. So he actually can't be in the ABCD study because he has metal in his mouth. Go figure. But it really does cause artifacts, not harmful to the kid unless they, aren't really well attached. But and when you're doing longitudinal studies, you have to just decide, what we have done in the past is just wait till the braces come off. Let us know the minute you have the appointment to take them off. So if we were supposed to study them, a year later and they have braces, let's do it 18 months later or whatever you can do about it. The other thing I think about is, and I'm pretty sure, but I haven't seen data on it, is that the braces are going on kids who have families who can afford the orthodontics, right? And so I'm not sure if there is sort of a bias. Well, in a way, maybe it's not a bad bias to get rid of more of the high SES kids whose parents can afford the braces, but it's something to think about that no one can avoid. It's a question that comes up anytime you're talking about a longitudinal study of kids in this age range. So those are the things that come to my mind. Again, not the detailed specifics on, motion, obviously the biggest one, but just to give you an idea that there are methods out there to help you deal with it after the fact, and that there are things you can do in advance to try to avoid losing data. And, again, one of the costs, and every hour is a cost, right? And if you have to spend an hour in mock scanning, it's certainly cheaper than an hour of crappy data in the real magnet. But you have to consider that within the time frame that you're looking at of doing your study. So it's an extra 20 minutes, half an hour that you have to think about. So does anyone have any questions about this part? Because now I'm going to start talking about just some of the payoff. Like, what kind of cool stuff can you do once you decide to take the hard job of scanning kids? Yep. And don't ask me how to do scrubbing. I'll send you Jonathan Power's paper.
So one of the things that my lab always struggles with is how do we walk the line between keeping the kids in the magnet versus knowing when they've reached their limit? And there doesn't seem to be, there's differences among every group, and even within the lab, different opinions about this. And we have these overly compliant kids that end up saying they're fine, but then we pull them out and they're like crying.
In tears. Yeah, it's a clinical judgment. I really, if they tell you, you know. If they say, again, I'm talking all about the ABCD. I'll show you a video in a minute that gives you a bigger overview. But some of my colleagues, we are recruiting some high-risk kids in the ABCD. And in this case, the high-risk sort of threshold is pretty low. It's kids with maybe some externalizing problems, not clinically diagnosed ADHD kind of stuff. But they figure out that button and they keep squeezing it. And, not much you can do. When they tell you, you know. But I agree, and I think there's also maybe a difference in the clinical training of the researcher. So this is just an observation from my own, but I think when you have researchers who maybe are clinicians, either psychologists or pediatricians or whatever, they probably have a different threshold as well. They're used to seeing, if they're used to seeing kids clinically, and you have to get in the magnet, you have to do this because we have to figure out if you have a brain tumor. They might have a different threshold for deciding, well, let's make the kid do it because it's the clinical. I have colleagues at Penn, University of Pennsylvania, and in Hawaii who are both physician scientists and who have recruited a huge amount of kids because, at least from my understanding, they'll just take every kid who comes into a well-visit clinic, and it's very, I don't know, being trained, as a primary researcher, clinical, not licensed neuropsychologist, I probably have a lower threshold to say let's get them out than someone who sees kids clinically. So there is no right answer unless they tell you, get me the heck out of here. We've had kids actually crawl out of the scanner while it was still running because they didn't know. Other questions? Yeah?
You have, if you've had any experience with or any opinions about the Enigma pipeline at coming from Lonnie, and just how, if you feel like that's a fine way to go about seeing like what structural scans should pass or fail and what you're going to use in your analysis.
I know the people very well who are developing that. I really can't talk to that from experience. I don't know. I just don't know. What I do know is that it's like huge amounts of data, big, large data that they process, and just from my experience, you may have different standards of validity versus reliability. So if you do something 100% reliably because it's all automated, then you don't have the human error. But then you have to question, or, at least consider the validity. So if it's doing everything the same way, but it's doing it wrong, it's a trade-off. And you know, what kinds of quality control can you do on 10,000 scans versus, you know, 200? You have different approaches. So, and I don't know how Enigma is dealing with pediatric data. So it can be different. Yeah, one other thing that I forgot to put a slide in here is it sounds silly, but when you have kids, let me see if I can find that, go way back. Their brains, kids' brains, the space between the skull, you know, the CSF around it is much smaller in kids, right? So boundaries that are typically used in automated, you know, skull stripping paradigms, it's a little bit harder to get it to work in kids. So a lot of times when you do an automated thing, you'll have big chunks of scalp still attached to the brain. And it's really because the boundary, you know, their heads are still expanding, their skulls are still expanding a little bit. So anyway, another thing to think about with kids, it's a little bit different than adults. So, yeah.
Hello? Okay, yeah. I guess on that point, I have two questions. One, we've been talking before about what template you should use for kids. And so I guess I'm curious what template you use for your kids' studies.
Right. So we use various templates. I mean, a lot of times what we'll do is use an individual from the data set as the standard, warp everyone to that, and then warp that to a more standard adult atlases. You know, and when you think about also with longitudinal studies, you want perfect registration, but if you're looking at change over time in kids, there's going to be a little growth. And I assume the same is true at the other end of the aging spectrum, where you're going to get some shrinkage. And, you know, if you get a perfect match, are you sort of, you know, erasing the growth that you want to see? Or, you know, because you've perfectly registered time 1 to time 2, you know, you would be losing evidence of growth. So it's a really complex thing, but from my experience, there's no, at least after age 5, there's no, and I know there are papers that prove this, that using a pediatric versus an adult template doesn't make as much difference after age 5. So in all of my many publications, I've never made a big deal about, oh, it has to be a pediatric atlas and you have to go find one after age 5, and that's the bulk of my work. So good question, but I don't think there's a solid answer.
And the other question is, often when doing kid imaging, you know, they do move a lot. So I'm wondering, we've had a lot of talks about motion and being very, very strict about motion.
Yeah.
I know myself, like, if I'm that strict, I throw away a lot of data.
Yeah.
So I'm curious to know what
I showed
we
you
should do.
some of our, standards for the T1 weighted data for structural. I mean, you can't do anything with a 5. Maybe a 2-3, you might be able to get something meaningful. Maybe, and you think about motion as well, that in the deeper structures, you have less of an artifact than you do when you move further out, because just think about the geometry of something moving. It's moving less around its axis, right? I have done a lot of studies with, like, for example, 6 minutes of resting state MRI. And it wasn't until a postdoc who had from University of Oregon, she had worked with Damien Fair, and when she came to my lab, and she was, her idea about what should be done was very different than mine. And I was like, what, we're going to throw all this data away? I mean, it's really the baby bathwater question, right? You certainly, I mean, I think in the past 2 or 3 years, it's become pretty clear that it would be really hard to publish something, at least with resting state, without saying you had a certain number of volumes and you did the scrubbing. But then there's, say, garbage in, garbage out. I don't know. It's a balance. I mean, you certainly. It's a balance. I think today I would say I want 10 minutes of pretty pretty good data throughout the volumes that are within volume motion and correct between volume. You could ask purists, right? Because I'm, God knows, don't want to publish garbage, and I wouldn't if I knew it was by any means, but I'm not one to say, if I don't have 12 minutes of pure, clean, motion-free resting state, then I have to toss it. I think it's a way, it's, different people have different standards, and I think maybe that people who study kids have to think about things a little bit differently than people who study adult populations. So I hope that was a very clear, concise, black and white answer to your question. So, I wanted to talk a little bit in my last few minutes. Clearly at this point I won't have time to talk about all the things that I wanted to show you. They're just nothing in great detail, but just tidbits of kinds of things. So I've talked about ABCD study for 45 minutes, and you might not even know what it is, so I'm going to show you a movie. And then I'll just talk a little bit about the kinds of studies we're doing that really are so exciting, and just thinking about these, studying developmental neurodevelopmental disorders. There's an obvious clinical implication. And when I started doing this back in the early 90s, I started looking at fetal alcohol, and then myself and others around that time, early mid 1990s, started saying, wait a minute, how can we interpret what we're seeing in these kids who have disorders if we don't know what's going on? Excuse me. If we don't know what's going on in the typical brain. So NIH would fund autism, they would fund all sorts of ADHD, but they wouldn't fund typical development. I mean, why would you give money to study kids who don't have a problem? So anyway, that changed, and it changed dramatically, I think. And here's an example of it. And I'm just going to show you a little movie that talks about the ABCD study. Hopefully it's not too boring for you. But while you're watching it, I'm going to get a cough drop out of my throat. We have the opportunity to be part of an incredibly important new study called the Adolescent Brain and Cognitive Development Study. We call it the ABCD study for short. This study is really important because for the first time, we're going to be studying 10,000 9 and 10-year-old children, all typically developing from all over the country. We're going to be following these kids over time for 10 years. We can take this same kid when they're 10, 11, 12, 20, and what we can measure are what we call trajectories of change in the brain that occur during this important developmental time period. The National Institutes of Health funded this study for us to get a real foundation of what normative development is in the brain, in cognition, in behavior.
My name is Trin, and I'm the project coordinator for Dr. Elizabeth Sowell's lab. If you are interested in this study, you would contact us, and we will tell you a little bit more about the study. If we determine that you are eligible, you would participate in several activities. One part is the MRI scan, which is a giant magnetic machine that takes pictures of your brain. And then you'll also be doing some questionnaires and answering some surveys and solving some puzzles with us. And we'll take a saliva sample, which means your child will get to spit in a tube.
What we do is brain imaging research. We use a big donut-shaped magnet, and it's called magnetic resonance imaging. It lets us see in great detail pictures of the inside of a kid's brain. One thing that's really important, and parents ask me all the time, is are there x-rays? Is it safe? Absolutely, completely safe. Magnetic resonance imaging doesn't involve any x-rays. I've put my own child in the magnet on many occasions, so it's completely safe. It's really important that we understand how the brain develops in typically developing children, and that will help us understand what's going on in the brain when things go wrong.
All right, well, thanks for coming in to participate in our research study today. Do you know why you're here?
Yes, I'm going to take a brain scan.
That's right. That's right. You're going to go in a special machine where we can take pictures of your brain so that doctors like me can better understand how you think and how you move. When we go downstairs and we're in our special camera, you're going to lie on a little skinny bed. The machine, as it's working, it has loud banging noises, and so the earplugs are there to protect your ears. You're going to have some headphones on. You're going to get to wear some goggles. Sometimes you're going to be watching a movie. Sometimes you're going to be looking at pictures of things that we want you to do something with, and sometimes you're just going to be sitting there quietly. The headphones have a little special button. So if at any time you have a question, you can push the button, okay, and ask the question. But you want to make sure you stay still. You want to be as still as you can.
Okay.
I'm a research associate.
Okay, I don't need to, oh, what did that do? I don't want to, bore you with the rest of it. But you get an idea, I think, from that movie, a little bit about what ABCD is about. But also just a little bit different when you're dealing with kids than when you're dealing with adults, and, the level of which you talk to the kids to make sure they sort of really understand what you're saying. So it's just a little bit different, and I think that illustrates a little bit of the difference. So in the few more minutes that I have, I'll just talk about a smattering of different studies that we've done. One thing I want to emphasize is, I talked a lot about most of the work that I have done is, starting at age, maybe as young as 5 and not younger yet. I'm not as brave as many who study babies, but from my understanding, early infancy is much easier to study than, say, the 1, 2, 3 years old, because you can't sedate typically developing kids, and I think it's hard to keep a 5-year-old still try a 2 or 3-year-old. But that said, I think, or I know, that a lot of dramatic changes are happening in the brain during later childhood and adolescence. There's a lot of signal going on to measure, and I think that one of the biggest things we do or are interested in is what accounts for that variability in signal, beyond just age, right? Why do some 8-year-olds look just like some 12-year-olds in the brain, and vice versa? A 12-year-old look like an 8-year-old, and is that brain structure or function? What's accounting for that variability? And so a lot of my work has focused on childhood and adolescent age range, and some of the really, I think, important work has shown, the impact of pubertal hormones. Again, this is an important thing in age range to study because it's when a lot of problems start happening, right, during adolescence. And there are sex differences in the types of disorders that you see when things go wrong. It might look pretty different in Johnny than it does in Susie. And so one thing that might help explain some of that variance could be the pubertal hormones, which we know have an impact on the brain. And some of our studies have shown, like the impact of testosterone, for example, has a very different impact and different impact on the brain in boys and girls. And looking at maps like this, you can start to think, well, maybe this helps me understand why boys in this age range, in the adolescent peripubertal age range, might have different problems to deal with. So if boys and girls have what I like to say is a different brain age, so say they're starting junior high and they're all 12 years old, right? And there's a lot of variability in and of itself, but boys' brains at 12 are looking very different than girls' brains at 12. Yet they're being asked to transition into a different environment, which requires a lot of more executive control, right? When you switch from elementary to junior high, there's a lot more demands on you, more is expected of you, and boys, we might expect a little bit different of an ability to comply with those sorts of new constraints or more freedom in boys than girls. And so just something to think about in studies that show what kinds of factors influence what's going on in the brain between individuals and in addition to age. So this is work from Megan Herding in my lab, and it's longitudinal change over time. So each of these lines is a person, and looking at volume change over time, and you can see that very different things are happening, say in total gray matter volume in, thank God Megan made the girls pink, because I can't read this, actually. Anyway, you see very different things happening in girls than boys based on Tanner stage, which is just a measure of physical sexual maturity, self-report from boys and girls. And you see different things in different regions of the brain with changes in puberty. And I like to, this is going to be very confusing, but I try to use it. So one thing that we see pretty often, myself and others, is sort of trajectories of change over time in, say we're talking about gray matter volume just as one sort of measure of a feature of the brain that might be meaningful in terms of that child's behavior. And we see, there are increases followed by decreases, and we see pretty consistently sex differences. This is actually a slide from Jay Geed from many years ago, 1999. The gray matter volume peaks at a different time in and later in boys and girls, and you start to wonder why. Well, let's think about hormones, because we know boys' puberty starts about 2 years later than it does in girls. And so anyway, using some of Megan's data to say, hey, look, the patterns are really different in boys and girls based on, say, level of testosterone or change in testosterone. So we know from animal studies that pubertal hormones have both activational and organizational effects on the brain early. And I think we think that organizational effects happen much earlier, and that the later impact of hormones is more activational, right? Not really building structure, but actually that's not really true. Sex hormones can have an impact of, being the stop gate, right? Stop growing and start declining. And when we see decline in development, we don't think of atrophy or decline as being a bad thing in development because, these kids are continuing to learn and develop into adults. So maybe decline, it has something to do with pruning away important connections, because you can't support all of the connections in the brain. So anyway, things to think about that are interesting and important to study. Some of my favorite, most important work that I pursue is looking at how the environment impacts the brain and development. And in LA, we live in a very diverse area. We've known forever that kids from lower SES tend to perform more poorly on cognitive measures in school. And, so my colleague, Kim Noble, and I conducted this collaboration in a very large sample of children to say why, what's going on. We knew it's kind of a no-brainer that it's in the brain, but really for the first time we were able to show that surface area, anyway, of the brain, how many wrinkles and folds does it have, is related to family income and parent education. But I think the most important thing that we take out of this is it's very much driven by the very low SES kids, at least in our sample. So the difference of $10,000 a year in family and increment increase. So if I gave you a $10,000 raise and you already made $150K a year, big deal. It's going to be an extra summer vacation or summer camp for the kid instead of. But when if you're making 25 grand a year, you're in poverty, and I give you 10 grand, it's going to make a huge difference in your quality of life, or it could. So the difference between summer camp and guitar lessons when you're already in upper middle class versus, do I pay the rent or buy food? So, what I'm looking at now in my current research and in the ABCD sample, things that I'm most interested in as being a scientist, not just being a data collection machine for the NIH, right? Nobody signed up for this study to recruit. Susan and I combined are going to try to recruit 1,000 9 and 10-year-old children in a 2-year period. And the whole study is 10,000, so we're going to have a hard job. But it will be worth it, because we get to say, what the hell, what is money buying? That's my interest anyway. So, what does it buy? Cleaner air. Okay, there have been studies showing links between air pollution and autism spectrum disorders, and in studies out of Barcelona and just typically developing kids showing relationships between exposure to air pollution and things in the brain, activity, function, and structure. And think about it, it's not the super wealthy people that live at the intersection of the 405 and the 101 within a mile of those freeways, right? And there are studies, there are experts at USC. Children's Hospital is the Department of Pediatrics for USC, so I'm a professor at USC. Anyway, I have colleagues at USC who are world-renowned experts in urban, the impact of air pollution on, not brains, I'm the brain person, but, you collaborating with these people, it's amazing. We're talking about putting these nanosensors that are proprietary, but apparently these nanosensors can measure air pollution as the kid's walking around in the environment, and then we can look, how does air pollution relate to the brain in kids in LA, because we're going to have a lot of variability. Another thing, and I'm going to skip over a bunch because I really only have 1 more minute. Maybe I should stop, but I want to show you one more thing that's really cool. My newest, most exciting thing, and I got the ABCD study to include asking parents for baby teeth. I have baby teeth in my purse because I saved them for my baby, and I was at an ABCD thing, and I thought, well, I'll bring the teeth because I'll show them. Look, I have them. I'm not crazy. It's kind of crazy to carry them around in your purse, but I forgot to put them back in where I keep them. Anyway, but the coolest thing is that you can measure, there are scientists, a colleague of mine at Mount Sinai in New York, can actually measure over time exposures from baby teeth, starting in the beginning of the 2nd trimester. So it's like, apparently, I'm new at this, but dentin grows around the teeth, starting in the beginning of the 2nd trimester, like rings in a tree. And my colleague, can measure over time through those rings of the tree exposure to things like, for example, lead, right? So we can get quantitative measures of exposure to lead in the kids that we're studying at age 9 and 10 in the ABCD sample, if their parents save teeth and are willing to share them with us, or if they're willing to save the next tooth that falls out, because kids keep losing teeth until they're about 12. Anyway, it's just so cool that you can look at something that happened in utero and compare it to, so right, kids who had more lead in utero have different brain and cognitive development than kids who had less lead. And that, of course, varies with SES. Anyway, that's my newest exciting thing. So just in summary, and I have no time for questions now. I don't know if you have another. I could have talked about more stuff. All right, let me talk about one. I thought I had just 1 hour. Well, do people want coffee or do they want to hear me blab? Okay, I'm blabbing. 5 more minutes. Anyway, just a little bit about another study, an area of really great interest to me is looking at fetal alcohol syndrome. And I show you this slide just to give you an idea of what it looks like. So this is a typical baby. This is the same baby you saw get in the magnet in the movie I just showed you. This is when he was about 1. I think it was his first birthday. He was very cute. But this is a baby with fetal alcohol syndrome. So the full syndrome of the disorder and the diagnostic features of fetal alcohol syndrome are facial dysmorphology. Characteristic are microcephaly, so they have a very small head. Think about Zika. Susan was asking me about that earlier today. Small eye openings, right? So small palpebral fissures. Smooth upper lips. We know we all have this little ridge here. Fetal alcohol syndrome. That's a characteristic feature of what we call the philtrum, and a thin upper lip. So those are hallmark features of fetal alcohol syndrome. And you can see these brains. There can be some really severe abnormalities to the brain other than just brains are smaller. Callosal dysgenesis or agenesis is much more common in fetal alcohol syndrome than other neurodevelopmental disorders. So, you can't tell just by looking at a brain, that kid has fetal alcohol. But we know it's about alcohol. Here we have my colleague, Kathy Sulik. It's just amazing. In addition to Susan, who's one of my academic idols, Kathy Sulik is another one because she studies these little teeny mouse fetuses that the size of these mouse fetuses would fit in within the zero on a penny. If you look at, say, a penny from 2000 or 2012, the zero in it, this brain of these little fetus mice would fit in that little tiny place. So that's one reason why she's an idol. But anyway, so the face is diagnostic, but you can see clearly from these animal models that the brain is also dysmorphic. So in this mouse with heavy prenatal exposure in what would be first trimester equivalent, has similar features, so small eye openings compared to this unexposed fetus, and the lack of this little groove, and I don't know what it's called in a mouse. I know in me it's a philtrum, but it's more like a groove. And anyway, abnormalities of the brain and face. And again, this is important. In animal models, we know we see these effects during a period of time where a human woman might not even recognize that she's pregnant. So there's a lot of controversy still, and frankly, among higher educated women, that they can damn well drink a glass of wine every day if they want, and there's no proof in the literature that it's going to cause fetal alcohol. And so I've written 2 editorial comments on these new sort of coming out of women, taking their power back, and we're not going to be patronized and told we can't have a damn glass of wine. And I don't disagree with that, but I think, to be clear, the truth of the matter is, from the scientific perspective, we don't know how much is enough to cause disorders. And I would argue that maybe we'd rather not know. Not know, meaning we'd rather not take the risk of what would be considered very low levels of exposure. What if something happened to Johnny? What if I decided, screw you to the overarching men who doctors tell us what to do? What if something happened? I would never know if it was because I chose that I'd rather have a glass of wine than be safe than sorry. Anyway, I will stop there. But it's controversial, and among higher educated women. But the interesting thing that I wanted to point out, that I'm also really pursuing a lot right now, I was telling Susan I'm writing a letter of intent to continue another 5 years of my fetal alcohol consortium that I'm part of, a multi-site study. What's really interesting is that, there's damage to the brain, clearly, without question, because alcohol is teratogenic. And if the exposure is in utero, when it happened, when the damage happened. But you can see the black lines here are typically developing kids, longitudinal studies, and the blue lines are fetal alcohol exposed, kids with fetal alcohol spectrum disorders. So what I'll point out is not all the details, but just that trajectories of change over time during childhood and adolescence are also different. And so why is that? We knew when the damage was, but brain development is sequential, right? Some things have to happen before other things can happen. And so if you damage a system at one point in development, it's going to have a trajectory of impact over time. But the other thing I want to point out, and you can see from like the SCS studies, stuff going on out here is impacting the way this is wiring during childhood and adolescence. So it's not just by the time your brain is done developing, whenever that is, and I would say well after age 25, right? People say, oh, your brain's done by the time you're, 20. No, more like 30. At 30, I think. And then the decline in aging every year gets a little bit later, because every year I interpret those smooth curves where the center of it moves forward as I age, knowing that it used to be 40, clearly. Now it's a little bit later. Anyway, I'm just joking. But think about what is going on in the environment of these kids with fetal alcohol that has a different impact. And so I have a postdoc who's doing studies looking at sex differences and pubertal hormones in fetal alcohol to try to explain what's going on that could be different in alcohol exposed than controls. And the last thing I'll show you is that there are, within, as you would expect, even within kids, whether you're exposed to alcohol in utero or not, things going on, what does money buy is the same question, whether you're exposed or not. But kids with prenatal alcohol might be more vulnerable to low SES than kids who didn't have that. So we're looking at interactions between exposure and, say, for example, family income, and we are seeing differences. These are work, in preparation, but also thinking about, what other things, like I already talked about, air pollution. We know lead goes along with SES, so we're going to be looking at proposing, anyway, to look at lead in the baby teeth of kids with exposure. And so there's just, I just want to say it's hard. It's hard work. I think it's harder, but I'm biased, right? I'm biased. I'm sure it's hard to study elderly, people with disorders of many kinds. But anyway, it's hard. But I just wanted to end with, it's really worth it. And, think of all the money that goes into cancer research and, aging research, and thinking about if there are things we can do. And all of it is with the hope, can we find things that we can change for the better, right? You can't just give every kid $1 million, right, to make their brains grow a little bit more. But what if we found out that, kids who exercise more, maybe that offsets things that are, free, or things that we can do as a society to help improve the lives of kids where, if we didn't do these studies, we wouldn't know. So I think this work is very fundable. It's very competitive, but it really is fundable, and I think you see it in society. You see the concerns about poverty, and every day you hear about it. All right, so I'm done. And questions, right?
In conclusion, I'm done. That's a great summary.
Wasn't that? Well, I did have a summary, but then you told me I could talk longer.
I did, and it was
So it
great
was
as well.
just really, kids' brains, movement costs money, lose data, you can do, prevention is key, put them in the mock scanner. The payoff, though, is in my opinion, huge, and it has a big societal impact, or it could, so it's worth it.
Does. Your work has been heavily publicized in the lay press as well as in featured news articles in Nature and Science. People actually care about this quite a bit.
And most evil, don't forget.
And most evil, yes. Any questions for the evil person in the room?
I was wondering how you're handling incidental findings in these children, because there must be a big
Okay,
issue.
yeah,
With this,
that's tough.
we just finished 4,000 children. It was really, we found a lot of things. So I was wondering what
Yeah.
your protocol is.
Yeah, different IRBs, like ABCDs, a huge multi-site study. It is not insignificant. I mean, so what we do at Children's is we ask parents to say, if it's going to be read by a radiologist, please provide us with the name of a pediatrician that we can communicate with if something's wrong. Okay. Say the mom doesn't sign it. Well, remember, we're dealing with a lot more low SES. Maybe she doesn't have a pediatrician. Or maybe she doesn't have the pediatrician's address or remember the name. We had one time found a kid who it looked like they might actually have multiple sclerosis. There were a lot of what looked like plaques, and this was, a 13-year-old kid, and the mom hadn't signed it. So, I mean, we had to go to heroic efforts because that was the kind of thing that at least the radiologist reading it, and maybe they should get treatment. So I know it's an important incidental findings. It's tough. I mean, what if you found like some sort of venous malformation that could blow at any minute, and there was no way to do anything about it, and you think about, would you want to know? I don't know. It's like, it's not trivial. So I don't know how to answer your question. Other than that, in ABCD and in other studies, we're coming up with sort of guidelines, and every scan will be read by a radiologist, and hopefully someone else will decide if it's important enough to tell. Like Chiari malformations come up all the time, and are they, just normal variant? Is it potential to cause problems? It's tough. So I don't have an answer, but I know it's an important issue.
Leave that as a checkbox option on the consent form about whether to inform the
Yes,
volunteers?
we do, actually. But again, that's where we say, if you want to know, give us the name of a pediatrician, and if they don't have that, I mean, the kid who we thought maybe had multiple sclerosis, we called the mom, left her messages. She never called back. And then at that point, you start wondering. Anyway, so but yes, a checkbox. But then if they say no and you see something that you know could be treated, it's tough.
So I was wondering if you could talk a little bit about the ways that you can ensure when your teens take their saliva samples, how that's stored, and then how it's going to be processed later. Because at my previous institution, we asked kids to take saliva samples, and depending on whether they freeze it or put it in the fridge and how they bring it back to us, it can affect how the sample degrades. And there are a lot of papers where they don't specify how they went about handling this, but that's a really crucial.
Absolutely.
Concern.
So it depends on what you want them for. In this case, for my big deals for pubertal hormones, and for pubertal hormones, they do have to be frozen relatively quickly, and they have to stay frozen until they are processed. And particularly estradiol degrades very, very fast at room temperature. So I know other it may be interested in things like cortisol, and time of day is important. And let me tell you, for girls, estradiol has fluctuations, monthly fluctuations, that, if you were going to do it really right, ways to do it really right in girls so that you can sort of account for monthly variation would be, menstrual timing, start and stop, but then that's hard because in girls early puberty there's a lot of irregularity. It's hard. But what we do in my lab is we have a little for the pubertal hormones, we have a little mini freezer. So we get the kid to spit, put it in the little mini freezer right away, and so then that freezes it to minus 80 or minus 20. Minus 20 would be okay for a period of time. And then whenever the RA has a break, they take the spit to a standalone freezer in the lab somewhere, not in my lab, but in the building. And then we ship it to, we use salometrics, so we ship it to them on dry ice, and we wait till we have, 30 or 40 samples before we ship it. So for things like cortisol, I think I'm not as expert in that, but my postdoc is actually, and she's proposing to do some cortisol at home samples at different times of day, because cortisol, you don't get the variability within a day may be greater than the variability over a year. So you really need to get a better idea. So good question. It depends on the question and what you want the spit for. DNA can sit on a shelf for a year, not refrigerated so.
And thanks very much for coming to join us. Really appreciate it. Great lecture.
Well, thank you.